Our universe is built on a scale that defies all human intuition. We look up at galaxies, those majestic islands of stars, and think we have glimpsed the largest things in existence. But the truth is far stranger. Galaxies themselves are merely the building blocks, the individual threads, in a tapestry of such staggering size that it rewrites the rules of reality. By staying until the end, you will gain a completely new mental map of the cosmos, one where our familiar galaxy is just a speck in a vast and bizarre architecture. We are about to journey through 25 of the strangest cosmic structures ever discovered, each one larger than entire galaxies, each one posing profound challenges to our understanding of the universe itself. How can a wall of galaxies exist that seems to break a fundamental law of cosmology? What mysterious force is pulling thousands of galaxies, including our own, toward a hidden point in space? The answers lie in a realm where filaments of dark matter weave through billion light-year voids, and where the very fabric of space-time might be etched with scars from the birth of creation. When you think of the word vast, what does your mind truly see? To comprehend these colossal entities, we must first understand the framework that contains them all. Our universe is not a random scattering of galaxies, not a uniform soup of stars. Instead, it is structured like a spider's web spun on a scale so immense it is almost impossible to picture. This is the cosmic web, the single largest organized structure we know of, a skeleton of reality woven from dark matter and lit by the fires of galaxies. If you could step back far enough, you would see a delicate, intricate network of luminous filaments, each one a highway of thousands of galaxies, all connecting at dense nodes like cosmic cities. And between these brilliant threads there is almost nothing. Enormous, dark, and nearly empty voids stretch for hundreds of millions of light years, regions of profound silence where a single galaxy would feel utterly alone. This web is not a static picture. It is a dynamic, flowing architecture that guides the very destiny of matter. Every galaxy, including our Milky Way, is part of this flow, carried along these filaments like a leaf caught in a gentle, billion-year current. How did this structure come to be? Its origins are etched into the first moments after the Big Bang. Tiny, random ripples in the density of the primordial universe, imperfections smaller than a single atom, were amplified by gravity over eons. Slightly denser patches pulled in more matter, growing into the nodes and strands we see today, while the less dense regions emptied out, becoming the great voids. This filamentary nature does more than just arrange galaxies, it dictates their evolution. Galaxies that lie along the busy filaments or at the crowded intersections tend to grow larger, faster, and more active, constantly fed by rivers of fresh gas flowing along these cosmic channels. Those isolated in the voids are often stunted, quieter, and older, starved of the material needed for new growth. So when we speak of the 25 strange structures larger than galaxies, remember they are not floating in empty space. They are distinct, awe-inspiring features within this greater web, like particularly massive knots, unusually long ropes, or startlingly vast empty chambers in the grand cathedral of the cosmos. But even within this grand cosmic web, some features stand out for their sheer, almost impossible size. One of the first to truly shatter our sense of scale was discovered hiding in the northern sky, within the constellations of Hercules and Corona Borealis. Astronomers mapping gamma-ray bursts, the most violent explosions in the universe, noticed a startling pattern. These brilliant flashes were not scattered randomly. Instead, they traced out a colossal, dense concentration stretching across an almost unthinkable distance. This was the Hercules-Corona Borealis Great Wall, a filament of galaxies so vast it measures approximately 10 billion light-years from one end to the other. To put that in perspective, the entire observable universe is about 93 billion light-years across. This one structure, a single thread in the web, accounts for more than 10% of the known cosmos. Its existence sent shockwaves through the field of cosmology because it directly challenges a foundational idea called the cosmological principle. This principle states that, on the largest scales, the universe should look roughly the same everywhere, and in every direction it should be homogeneous and isotropic. Finding a structure of this magnitude is like looking at a vast ocean and discovering a single wave taller than the distance between continents. It suggests that maybe, just maybe, the universe is not as uniform as we thought. The debate about the Great Wall continues to this day. Is it truly one coherent structure, a single, connected filament of galaxies bound by gravity? Or is it a chance alignment, a trick of perspective where several smaller clusters simply appear connected from our viewpoint? The question remains open, a testament to the difficulty of mapping the architecture of reality itself. Yet its very proposal forces us to confront a humbling truth. Our models of the cosmos are built from the tiny fraction we can see, and every time we push the boundaries of observation, we risk finding something that does not fit. The Hercules-Corona Borealis Great Wall is a monument to that uncertainty, a ghostly silhouette on the map of everything that whispers we have only just begun to measure the true grandeur of our home. While the Hercules-Corona Borealis Great Wall currently holds the record for sheer immensity, its discovery was built upon the shoulders of another structure that first tore the rulebook in half. 2 decades earlier, a painstaking map of the cosmos was being assembled by a telescope in New Mexico, part of the Sloan Digital Sky Survey. Its goal was simple yet monumental: to catalog millions of galaxies and chart their positions. What it revealed was anything but simple. Staring back from the data was a colossal ribbon of galaxies, a filament so dense and long it was immediately dubbed the Sloan Great Wall. This structure, stretching for nearly 1.4 billion light-years, became the largest known thing in the universe at the time of its discovery in the early 2000s. To grasp that scale, if you could travel at the speed of light, it would take you over 1 billion years just to go from one end to the other, a journey through a single concentration of tens of thousands of galaxies. Its composition is a textbook example of the cosmic web's architecture, a stunningly long and massive filament connecting several enormous galaxy clusters, like glittering beads on an impossibly long string. The discovery of the Sloan Great Wall sent a seismic shift through cosmology. Before its identification, theoretical models had suggested an upper limit to how large gravitationally bound structures could grow in the time since the Big Bang. The Sloan Wall smashed right through that theoretical ceiling. It proved that the universe was capable of organizing matter on scales far grander than anyone had dared to predict, forcing scientists to re-examine their assumptions about the growth and distribution of matter in the cosmos. When we compare it to the later discovery of the Hercules-Corona Borealis Great Wall, we see a clear and thrilling progression. The Sloan Wall was a shocking anomaly that expanded our mental horizon of what was possible. The Hercules-Corona Borealis Wall then took that expanded horizon and stretched it even further by an order of magnitude. One revealed that our universe builds walls of galaxies. The other suggested that some of those walls might be so vast they challenge our most fundamental ideas about the cosmos itself. This is the rhythm of discovery, where each new, unimaginable structure becomes a benchmark, only to be surpassed by something even more unimaginable, waiting patiently in the dark. But the universe's capacity for surprise does not stop with walls of galaxies. It extends to the most violently luminous objects ever seen, and how they gather together in ways that seem to defy logic. Deep in the constellation of Leo, astronomers have mapped a congregation of quasars so immense it has earned the name the Huge-Large Quasar Group. To understand why this is so strange, we first need to know what a quasar truly is. Imagine the core of a galaxy where a supermassive black hole, weighing billions of times more than our Sun, is actively feeding. As colossal amounts of gas and dust spiral inward, they are heated to millions of degrees, creating an accretion disk that shines with the brightness of 1 trillion stars. This is a quasar, a beacon so powerful it can outshine its entire host galaxy and be seen across the universe. They are the lighthouses of the early cosmos, marking the locations of young, chaotic, and incredibly energetic galaxies. Normally, quasars are scattered far apart as such extreme activity is rare. The huge large quasar group shatters that expectation. It is not a single object, but a collection of 73 quasars, all bound within a region of space roughly 4 billion light-years across at its longest dimension. This structure is so large that light, traveling at its universal speed limit, would need 4 billion years to cross from one side to the other. The sheer density of these brilliant monsters in one place is the heart of the mystery. According to our standard models of how the universe evolved, matter in the early cosmos should have been distributed more smoothly, for so many quasars, each requiring a massive galaxy with a voracious black hole. To form so close together in such a young universe stretches statistical probability to its breaking point. It is like rolling a pair of dice and getting double sixes not just once, but 73 times in a row. This concentration suggests that the early universe might have been far more clumpy and uneven on the largest scales than we ever predicted. The huge large quasar group stands as a profound statistical anomaly, a cluster of cosmic lighthouses that seem to shine a light not just through space, but on a potential flaw in our understanding of how the grandest structures first took shape. The huge large quasar group is not an isolated case. Decades before its discovery, another gathering of these brilliant monsters was already hinting that our cosmic maps were incomplete. This is the Claus-Campusano Large Quasar Group, a chain of 34 quasars identified in the southern sky back in 1991. Its existence was a quiet revolution, a first glimpse of something profoundly unsettling. At over 2 billion light-years in its longest dimension, this structure was, for its time, the largest coherent formation ever observed in the universe. Its scale alone was staggering, but its true significance was more subtle. The Claus-Campusano group was one of the earliest observational clues that matter in the universe might not be distributed as smoothly as the cosmological principle suggested. It was a statistical outlier, a concentration of incredibly rare objects that seemed too large and too dense to have formed by random chance within the standard model of cosmology. Think of it as finding a perfectly straight line of 34 active volcanoes, each 1,000s of miles apart, stretching across an entire continent. The odds of that happening naturally seem impossibly low. This is the challenge the Claus-Campusano group presented. It forced astronomers to ask a difficult question. Were we simply seeing a rare but permissible fluctuation in an otherwise uniform cosmos? Or was this a sign that the universe inherently favored building structures on scales that our theories could not easily explain? This single discovery helped pave the way for a new era of skepticism and curiosity. It demonstrated that quasars, those brilliant beacons, were not just isolated points of light. They could serve as tracers, revealing the underlying skeleton of the cosmos, highlighting where matter and the supermassive black holes they harbored were gathered in astonishingly vast assemblies. The Claus-Campusano-LQG was the first faint signal that the universe's largest structures might be even larger and stranger than we had dared to suppose, a hypothesis that every subsequent discovery has only served to strengthen. The search for these immense structures often leads to the most violent events in the cosmos. Gamma-ray bursts are the universe's ultimate fireworks, fleeting explosions of incomprehensible energy that outshine entire galaxies for a few brief seconds. They are thought to signal the catastrophic births of black holes or the collisions of ultra-dense stellar remnants. For astronomers, these brilliant flashes are more than just spectacular displays. They are cosmic signposts marking the locations of distant galaxies in the early universe. By mapping their positions, we can trace the underlying distribution of matter on the grandest scales. And in 2015, this map revealed something that left researchers utterly speechless. A team analyzing data from orbiting gamma-ray observatories noticed 9 of these bursts, all at roughly the same immense distance from us, approximately 7 billion light-years away. But they were not scattered randomly. They formed a near-perfect colossal ring on the sky, a circle with a diameter of 5.6 billion light-years. This is the Giant Gamma-Ray Burst Ring. To visualize this, picture a circle so vast that light would need 5.6 billion years to travel from one side to the other. Within this unimaginable circumference, 9 cataclysmic events, separated by billions of years in time, had all occurred in galaxies arranged in this impossibly large, geometrically perfect formation. The symmetry is the heart of the mystery. Our universe builds clusters, filaments, and walls, all tangled and web-like. It does not, according to any of our models, build near-perfect circles on this scale. Such a ring is simply not predicted by any theory of cosmic structure formation. Gravity and the initial conditions of the Big Bang do not naturally produce giant, symmetric hoops of galaxies spanning a significant fraction of the observable universe. So what could possibly create it? One speculative idea points to a cosmic phenomenon so vast it sounds like science fiction, a remnant from the universe's very first moments. In the instance after the Big Bang, theorists believe space-time itself may have undergone a phase transition, shifting from one state to another, much like water freezing into ice. If this happened in a chaotic way, it could have created defects in the fabric of reality, topological knots or cracks frozen into the expanding cosmos. One such hypothetical defect is called a cosmic string, a flaw in space-time thinner than an atom but possessing immense mass stretching across the entire universe. If one of these strings existed and oscillated, it might have created a spherical shock wave that propagated outward, compressing matter into a shell, a perfect expanding ring of galaxies. The Giant GRB Ring could be the first observational hint of such an exotic relic. A fossilized imprint of the universe's birth throws on a scale we are only now beginning to perceive. It stands as a silent geometric question mark against the dark, a shape that should not exist, challenging us to rethink not just how structures grow, but what scars the newborn universe may have left upon itself. The universe seems to have a particular fondness for shapes that defy our expectations. In the constellation of Boötes, the herdsman, a discovery was made that adds another profound layer to this mystery. Known simply as the Giant Arc, it is a graceful, crescent-shaped filament of galaxies that stretches an astonishing 3.3 billion light-years across the sky. This is not a solid wall, but a vast, coherent curve of galaxy clusters, gaseous hydrogen clouds, and dark matter, tracing a path through the cosmos that appears almost purposeful in its symmetry. Its discovery was a triumph of patient, meticulous observation. Astronomers did not see the arc directly, for its individual galaxies are far too faint. Instead, they mapped its presence by using distant quasars as cosmic flashlights. As the brilliant light from these quasars travels billions of light years toward Earth, it passes through the sparse gas that permeates the giant arc. That gas absorbs specific wavelengths of light, creating a unique fingerprint, a shadow in the quasar spectrum. By observing this telltale absorption in the light of tens of thousands of quasars, researchers could trace the outline of the intervening structure, revealing its staggering scale and crescent form. The sheer coherence of the giant arc is what makes it so challenging to explain. Like the giant gamma-ray burst ring, it presents a shape, a smooth, sweeping curve on a multi-billion light-year scale, that our standard models of cosmic evolution struggle to produce. Gravity, acting on random initial imperfections, tends to build lumpy clusters and tangled filaments, not elegant, persistent arcs. Its existence suggests that the seeds of the largest structures may have been sown with a level of organization or a specific type of fluctuation that we have not yet accounted for. This arc hanging silently in the depths of space is more than just a collection of galaxies. It is a question about the initial conditions of everything. It asks us whether the universe's first moments imprinted patterns of a scale and elegance we are only now beginning to glimpse, patterns that governed where galaxies would bloom billions of years later. Every time we find a structure like this, a wall or a ring or an arc, we are not just mapping the present universe, we are reading a fossilized record of its explosive birth, and the story is proving to be far more intricate and beautiful than we ever dreamed. Yet for all the awe these immense walls and arcs inspire, the cosmic web is defined as much by what is absent as by what is present. If filaments are the glittering threads, then voids are the dark, expansive gaps in the tapestry. And none is more famous or more profoundly empty than the Boötes void. Discovered in the early 1980s, this region of space is a staggering spherical emptiness approximately 330 million light-years across. To cross it at the speed of light would require a journey lasting longer than the time since dinosaurs first walked the Earth. Within this colossal volume, a space that could comfortably contain tens of thousands of galaxies like our Milky Way, astronomers have found only a scant few dozen. It is a cosmic desert of almost unimaginable scale, a sphere of near nothingness where a single galaxy would see only darkness in every direction for hundreds of millions of years. Voids like this one are not accidents, they are the essential counterpoint to the dense filaments and walls. They are the bubbles in the foam of the universe, regions where the initial density fluctuations after the Big Bang were slightly lower than average. As gravity pulled matter into the denser regions over billions of years, it siphoned material away from these underdense areas, leaving them emptier and emptier. The Boötes void is not completely barren, however. The handful of galaxies found within it are often isolated, peculiar, and fascinating to study. They are like lone survivors in a vast, empty ocean, evolving in profound isolation without the frequent galactic collisions and interactions that shape their cousins in the crowded filaments. Their very existence poses a puzzle. How did these few galaxies manage to form at all in a region so starved of the raw materials for star formation? Their presence hints that even the great voids are not perfectly smooth. They contain faint, wispy tendrils of the cosmic web, subtle bridges of gas and dark matter along which these lonely galaxies may have migrated or formed. The Boötes void teaches us that understanding the universe's largest structures requires listening to the silence as much as mapping the light. It is a reminder that emptiness on a cosmic scale is not passive. It is an active, sculpted feature that shapes the destiny of every galaxy that drifts along its dark borders, a vast and quiet chamber in the architecture of everything. While the Boötes void is a profound emptiness, another void in the cosmos might hold the key to one of the universe's most enduring and chilling mysteries. Far off in the constellation of Eridanus, the river, lies a strange and unsettling feature not in the distribution of galaxies, but imprinted on the very first light of creation. This is the CMB Cold Spot, a region in the cosmic microwave background radiation that is significantly colder than its surroundings. The cosmic microwave background is the afterglow of the Big Bang, a nearly uniform bath of microwave radiation that fills every corner of the sky, a snapshot of the infant universe when it was just 380,000 years old. Most variations in its temperature are incredibly tiny, mere millionths of a degree, representing the seeds of future galaxies. The Eridanus cold spot, however, is an anomaly on a different scale, a large circular patch that is conspicuously, mysteriously cold. For years, its existence baffled cosmologists. Could it be a statistical fluke, a rare but possible random fluctuation in the primordial soup? Or was it a sign of something truly exotic, perhaps even evidence of a collision with another universe? Before reaching for such extraordinary ideas, scientists proposed a more local, though still colossal, explanation. The leading theory suggests this cold spot is not a feature of the ancient universe, but a shadow cast by a truly vast structure in the more recent cosmos. This is the proposed Eridanus supervoid. Imagine a photon, a particle of light from the CMB, beginning its 13.8 billion year journey to our telescopes. For most of that trip, it travels through a universe that is relatively evenly distributed. But if, during the last several hundred million years of its voyage, it passes through an immense region of below-average density, a supervoid, it encounters a landscape where gravity's pull is unbalanced. As the photon enters the underdense region, it must climb out of a gravitational well that is shallower than average. This process, known as the integrated Sachs-Wolf effect, causes the photon to lose a tiny amount of energy. Over the immense span of the supervoid, that energy loss adds up, and when the photon finally reaches us, it appears slightly redder or colder than its counterparts that traveled through normal space. The Eridanus supervoid, then, would act as a colossal cosmic filter, cooling the ancient light that passes through it. The controversy lies in the numbers. Astronomers have indeed found a large underdense region in the direction of the cold spot, but there is a fierce debate over whether it is sufficiently vast and empty to account for the dramatic temperature drop we observe. Some studies suggest the known void is simply not big enough. Its gravitational effect would be too weak to create such a pronounced cold spot. This leaves the mystery wide open. Is the Eridanus supervoid larger and emptier than our current maps show, waiting to be fully measured? Or is the cold spot a genuine relic of the universe's birth, a clue to physics beyond our standard model? This cosmic chill reminds us that the universe's history is written in layers, and sometimes the most ancient light carries the fingerprints of structures that formed billions of years later, a ghostly imprint of emptiness on the face of creation. This concept of a local void brings the mystery shockingly close to home. The grandest structures we have discussed seem like distant abstractions, but what if our own galaxy, the Milky Way, is not in an average part of the cosmos? What if we are floating inside one of these immense bubbles? This is the provocative claim of the KBC void, named for the researchers who proposed it. Evidence is mounting that we may reside in a local underdensity, a void roughly 2 billion light-years across, where the density of galaxies and matter is about 20% lower than the overall cosmic average. We are not in a place like the desolate Boötes void, but we might be in a significant suburban emptiness, a cosmic neighborhood that is less crowded than it should be. This idea emerged from meticulous surveys of galaxy distributions. When astronomers map the cosmos in every direction from our vantage point, they find that galaxies appear to be fleeing away from us faster than our best models of universal expansion predict. One compelling explanation is that we are sitting in a gravitational trough. Because there is less matter in our immediate supercluster to pull on us gravitationally, the expansion of space itself is pulling the surrounding denser regions away from us more forcefully, like a gentle current carrying us away from a heavier anchor. This local hole has profound implications for one of the most heated debates in modern cosmology, the measurement of the Hubble constant. This constant describes the rate at which the universe is expanding. There are two primary ways to measure it, one using the ancient cosmic microwave background and another using relatively nearby stars and supernova. These two methods have persistently yielded different results, a discrepancy known as the Hubble tension. If we are indeed inside the KBC void, it could resolve this tension. Local measurements would be subtly skewed by our underdense environment, making expansion appear faster in our neighborhood than it truly is on a universal scale. It is a humbling and radical notion. Our entire view of the cosmos, the foundation upon which we measure its age, fate, and composition, might be slightly distorted because we are looking out from a quiet, sparsely populated corner. We have spent centuries mapping the stars, only to discover that our very address in the universe may be a key piece of data we have long overlooked. Our cosmic address just received a stunning and profound update. For decades, we believed our home was the Virgo supercluster, a gathering of galaxy groups with our Milky Way on its outskirts. But that map was incomplete, drawn only from our static view of positions in the sky. A revolutionary new way of seeing revealed our true home is far grander. A continent of galaxies we now call Laniakea, a Hawaiian word meaning immense heaven. This structure is not a simple cluster, but a vast gravitational watershed, a cosmic basin where the flow of galaxies defines the territory. Imagine a sprawling mountain range where every river, stream, and trickle of water flows downward toward a single central valley. In Laniakea, galaxies are those rivers of stars, and their collective motion points toward a mysterious, powerful focal point of gravity known as the Great Attractor. By meticulously charting the subtle, three-dimensional motions of over 8,000 galaxies, astronomers could trace these flows. Instead of just plotting where galaxies are, they mapped where they are going, revealing the invisible gravitational landscape that shapes their journeys. The boundaries of Laniakea are not walls, but the gravitational divides where the flow of galaxies shifts direction, turning toward another, neighboring supercluster basin. Within this immense heaven, approximately 100,000 galaxies are all part of the same gravitational family, all drifting on currents that lead toward the same hidden destination. Our Milky Way is no longer a suburb of Virgo. It is a participant in a continental migration, a single starry leaf floating on a river that includes the massive Virgo cluster itself, all moving toward an unseen pull. This discovery fundamentally changed our perspective. We are not just in a cluster of galaxies, we are part of a dynamic, flowing structure so large that light takes over 500 million years to cross it. Laniakea is the majestic supercluster we call home, a testament to the fact that to understand our place in the cosmos, we must learn to read not just the stars, but the silent, relentless currents that carry them. But where exactly are these cosmic currents carrying us? The ultimate destination of Laniakea's Great Migration lies in the direction of the constellation Centaurus, toward a gravitational titan known as the Shapley supercluster. This is the single most massive concentration of matter we have identified within 1 billion light-years of Earth. If Laniakea is our immense home continent, then the Shapley supercluster is a neighboring, far more densely packed supercontinent, and its immense gravity is tugging on every galaxy in our local universe. Its sheer mass is staggering, composed of dozens of massive galaxy clusters, each containing thousands of galaxies, all in the process of a slow-motion, billion-year collision. This isn't a static pile of stars, it's a dynamic, chaotic metropolis in the making, where clusters are streaming together along vast filaments, their individual galaxies mingling in a gravitational dance that will eventually forge one of the largest bound structures in the cosmos. The sheer density of this region warps the space around it, creating a profound gravitational well that influences the motion of galaxies across an astonishing volume. Our own local group, along with the entire Laniakea supercluster, feels this pull. The mysterious Great Attractor that defines the heart of Laniakea is itself being pulled toward the even greater mass of Shapley. Think of it as a vast hierarchical tug of war. Individual galaxies are pulled into clusters, clusters are pulled into superclusters like Laniakea, and superclusters are themselves drawn toward the most massive concentrations like Shapley. This supercluster's influence is a dominant force in what astronomers call our peculiar velocity, the component of our motion through space that is not due to the overall expansion of the universe, but to the specific gravitational tugs of nearby mass. In essence, the Shapley supercluster is a primary reason our galaxy is not simply coasting with the expansion of space. We are being actively steered by the invisible architecture of matter on the grandest scales. Observing this colossal merger in progress offers a glimpse into the far future of our own cosmic neighborhood, a preview of what will happen when Laniakea and other superclusters eventually draw together under gravity's relentless influence. Yet this gravitational tug-of-war is just one part of an even larger story, a narrative written across a filament so immense it connects entire superclusters into a single, sprawling entity. This is the Pisces-Cetus supercluster complex, a web-like structure that reveals the true, interconnected nature of the cosmos on the grandest scales. Think of the cosmic web not as a flat tapestry, but as a three-dimensional sculpture made of bundled threads. Within our local universe, the Pisces-Cetus complex is one of the thickest, most prominent of those bundles. It is not a single supercluster, but a filamentary network that strings together several known superclusters, including our own Laniakea, into a loosely connected megastructure spanning roughly 1 billion light-years. Its name comes from the constellations where its densest knots are observed, a sprawling river of galaxies flowing through Pisces and Cetus, the sea monster. Within this complex, individual superclusters are not isolated islands. They are like major metropolitan areas linked by vast, luminous highways of galaxy groups and sparse filaments. Our Laniakea supercluster, with its 100,000 galaxies, is just one constituent part of this greater complex, a dense node where several of these cosmic highways intersect. The Virgo cluster, which we once thought was the center of our local universe, is merely a busy suburb within Laniakea, which itself is a neighborhood within the Pisces-Cetus filament. This hierarchical nesting reveals a profound truth about cosmic structure. There is often no clean boundary between one structure and the next. Where does Laniakea end and the neighboring Perseus-Pisces supercluster begin? The distinction becomes blurry at these vast scales, as the filamentary bridges between them are themselves made of galaxies and dark matter. The Pisces-Cetus complex demonstrates that the cosmic web is a continuous fabric. What we label as a discrete supercluster is often just a temporary concentration within an ever-flowing, ever-connected system, a local density peak in a river of stars that has no real beginning or end. Studying this complex is like trying to map a single mountain range while standing on one of its peaks. The structure extends far beyond our immediate horizon, reminding us that our perspective is always local, and the true architecture of reality unfolds on scales that continually escape our full view. This grand migration points toward a single, powerful mystery at the heart of our local universe. All the flowing motion within Laniakea converges on a specific point in intergalactic space, a gravitational focal point we call the Great Attractor. It is not a brilliant quasar or a visible cluster of galaxies. Instead, it is an anomaly, a profound tug in the dark inferred entirely from the peculiar motions of everything around us. For decades, astronomers have tracked how galaxies, including our own Milky Way, are not simply receding with the expansion of the universe. They possess an additional velocity, a sideways drift, and this drift shows a startling pattern. Thousands of galaxies across a vast region of space are all streaming toward a point in the constellation of Norma, the Carpenter's Square, as if pulled by a cosmic tide. The challenge in solving this mystery is frustratingly literal. This exact region of the sky lies directly behind the dense plane of our own galaxy, where the dust, gas, and stars of the Milky Way's disk create a thick visual curtain. It is like trying to identify a distant mountain peak while standing in a dense fog. Our view is heavily obscured, making it extraordinarily difficult to see what mass could possibly be generating such a powerful pull. Early observations could only detect the foreground of our own galaxy, leaving the source of the attraction a profound enigma. Was it a single, unimaginably massive object hidden there, a monster lurking in the galactic shadows? The answer, as we slowly peered through the fog, proved to be both more complex and more fascinating. Detailed surveys using wavelengths of light that can penetrate the dust, like infrared and radio, have gradually revealed part of the picture. A significant portion of the gravitational pull we feel is now attributed to the immense mass of the Shapley supercluster, which lies beyond the Great Attractor's direction. But here is the crucial twist: even after accounting for Shapley's mighty tug, the numbers do not fully add up. A significant component of the motion remains unexplained. There appears to be additional, unseen mass concentrated in that obscured direction, mass that is not accounted for by the galaxies we have so far managed to catalogue. This suggests the Great Attractor is not a single hidden object, but rather a dense knot in the cosmic web, a confluence of several massive clusters and dark matter filaments that together create a gravitational well deep enough to steer the motion of superclusters. The mystery is no longer about a single hidden monster, but about the detailed architecture of this hidden nexus. What specific clusters and filaments compose it? How much dark matter is woven into that node? The Great Attractor endures as a powerful reminder that some of the most fundamental forces shaping our cosmic journey remain partially veiled, hidden behind the very stars of our home, waiting for our instruments and ingenuity to finally bring them into full view. The Great Attractor pulls, but gravity is not the only sculptor of our cosmic journey. For every immense concentration of matter, there must be a corresponding void, and it is this dance between the dense and the empty that truly dictates the flow of galaxies. Recent research has revealed a profound counterpart to the Great Attractor, a structure defined not by what it contains, but by what it lacks. This is the Dipole Repeller, a vast cosmic underdensity, an emptiness so immense it exerts a kind of negative gravitational influence. Picture the universe as a landscape of hills and valleys made of mass. The Great Attractor is a towering mountain range, its gravity pulling everything toward it. The Dipole Repeller, located in the opposite direction of the sky, is a correspondingly deep and expansive valley. Because there is so little mass there, its gravitational pull is exceptionally weak. In the grand cosmic tug-of-war, the stronger pull from the dense regions like the Shapley supercluster and the Great Attractor doesn't just attract us, it also means we are being pushed away from the under-dense void by comparison. It is the relative lack of pull from one direction that creates the effective push from the other. This repeller is not an anti-gravity force, but a consequence of gravity's absence. If you are floating in a swimming pool and someone on one side pulls you toward them, you are also, from your perspective, being pushed away from the opposite, empty side. The Dipole Repeller is that empty side on a cosmic scale, a void hundreds of millions of light years across where the density of galaxies is remarkably low. Its discovery came from meticulously mapping the motions of thousands of galaxies and asking a critical question. Could the observed bulk flow, the collective drift of all these galaxies toward the Great Attractor, be explained by known concentrations of mass alone? The answer was no. To fully account for the speed and direction of this universal drift, astronomers had to include the gravitational effect, or rather the lack thereof, of a major underdensity in the opposite celestial hemisphere. The Dipole Repeller provided that missing piece. This interplay between attractor and repeller gives us a more complete picture of the forces acting upon our local supercluster. We are not simply falling toward a single point, we are sliding down a slope, away from a region of profound emptiness and toward a region of immense density. It is the combined landscape that sets our course. This understanding transforms our view of cosmic motion from a simple attraction to a complex migration shaped by the full topography of the universe, a journey guided as much by where matter is not as by where it is. Hidden in plain sight, directly behind the dazzling plane of our own galaxy, lies a structure that may rival even the legendary Sloan Great Wall. This is the South Pole Wall, a curtain of galaxies so immense it stretches for at least 1.4 billion light-years across the southern celestial hemisphere, a discovery so recent it was only formally mapped in the year 2020. For centuries, this colossal feature remained invisible to us, not because it was too far away, but because it was perfectly positioned behind a cosmic blind spot known as the zone of avoidance. This is the thick band of dust, gas, and brilliant stars that constitutes the disk of our Milky Way, a luminous veil that obscures nearly 20% of the extragalactic sky. Trying to see galaxies through it is like trying to spot distant mountains through a blinding, ground-level fog. The foreground glare of our own home completely washes out the view. The traditional method of cosmic cartography, which relies on measuring the light from individual galaxies, simply failed here. To unveil the South Pole Wall, astronomers had to become cosmic detectives, using a clever and indirect technique that reads the universe's hidden motions. Instead of looking for light, they mapped the subtle gravitational influence of unseen mass. They did this by meticulously cataloging the peculiar velocities of thousands of galaxies that we can see, those above and below the obscuring band. Every wiggle in a galaxy's motion, every deviation from the smooth expansion of the universe is a clue. By tracking these motions in 3 dimensions, scientists could infer the gravitational landscape pulling on them, essentially creating a topographical map of mass based on how things are moving. This technique, called peculiar velocity mapping, revealed a staggering gravitational slope. The galaxies were all being subtly tugged by an enormous concentration of mass hiding directly behind the Milky Way's disk. When they translated this gravitational signal into a 3-dimensional model, the South Pole Wall emerged from the shadows, a filament of staggering proportions, a dense concentration of galaxy clusters and dark matter that forms one of the most significant mass concentrations in our entire local universe. Its discovery is a triumph of inference over direct observation, proving that some of the universe's grandest monuments are still being discovered not by looking deeper, but by learning to see in an entirely new way. The wall's significance is immediate and profound. Given its proximity and immense mass, it is a major player in the cosmic tug of war that dictates the motions of our own galactic neighborhood. The bulk flow of galaxies we are part of, that journey toward the Great Attractor, is not governed by a single pull. It is the net result of multiple immense tugs and pushes, and the South Pole Wall is now understood to be one of the primary gravitational anchors in this complex equation. Its mass contributes significantly to the local gravitational field, helping to explain the precise speeds and directions of galaxies for hundreds of millions of light-years around. Finding it is like discovering a hidden mountain range that explains why all the rivers in a continent flow the way they do. The wall's location, so perfectly obscured, also serves as a humbling reminder. Our view of the cosmos will always be partial, framed by the accidental orientation of our own spiral galaxy. For every magnificent structure we have catalogued in the clear northern skies, there may be another, equally grand, waiting in the southern obscurity, its presence only felt through the silent, persistent pull it exerts on everything we can see. The universe's hidden architecture often reveals itself through the echoes of its own birth. One of the most profound of these echoes is not a structure of matter, but a frozen ripple in time, a standard ruler etched into the cosmos when it was a seething plasma of particles and light. In the first few 100,000 years after the Big Bang, the universe was a dense, hot soup where protons, electrons, and photons were tightly coupled, constantly pushing and pulling against each other. This created sound waves, literal pressure waves that propagated through the primordial plasma. When the universe cooled enough for atoms to form, the photons streamed away, and those waves froze in place, imprinting a specific scale on the distribution of matter. This is the Baryon acoustic oscillation, a cosmic fingerprint with a predictable size of about 500 million light-years. It acts as a natural yardstick, a ruler we can use to measure the geometry and expansion history of the universe with incredible precision. By looking for this characteristic scale in the clustering of galaxies, astronomers can not only measure vast distances but also uncover the grandest structures that align with this ancient pattern. And in doing so, they discovered a colossus that had been hiding in plain sight. The Boötes Great Wall is not a simple, singular wall like its namesakes. It is a complex, three-dimensional superstructure, a sprawling network of superclusters and filaments revealed by the Baryon Oscillation Spectroscopic Survey. Its discovery was a direct result of using baryon acoustic oscillations as a mapping tool. By meticulously measuring the positions of over 1 million galaxies, the survey could detect the subtle statistical preference for galaxies to be separated by that 500 million light-year scale. Within that detailed map, a pattern emerged: an immense concentration of matter stretching for at least 1 billion light-years. A web of interconnected galaxy clusters and groups that represents one of the most significant mass concentrations in the nearby universe. Its immense size and coherent structure make it a landmark in the cosmic web, a testament to how the tiny, frozen sound waves of the infant universe ultimately seeded the locations of its largest modern-day monuments. What is truly remarkable is the dual role of the baryon acoustic oscillation here. It was both the tool that allowed us to discover the Boötes Great Wall and the ancient physical process that helped create its underlying pattern billions of years ago. This means we are seeing a direct link between the quantum fluctuations of the first instant and the majestic architecture of the present, a connection written in the positions of 1 million galaxies and measured with a ruler born from the universe's first sound. Far to the south, in the faint constellations of the Clock and the Net, lies a gravitational anchor of almost incomprehensible scale. The Horologium Reticulum supercluster is a distant metropolis of galaxies, a sprawling assembly of mass so immense it exerts a tangible pull on the cosmic flows around us. While Laniakea is our home supercluster, Horologium Reticulum is a neighboring titan, a dense concentration of dozens of rich galaxy clusters all bound together by their mutual gravity. Its distance is staggering, roughly 900 million light-years away, yet its sheer mass makes it a dominant feature in the gravitational landscape of our local universe. To stand within it would be to witness a sky ablaze with the combined light of thousands of galaxies, each cluster a brilliant hub of stellar activity, all slowly drawing together in a merger that will last for eons. This supercluster's location is not random. It holds a crucial key to a larger puzzle. It lies almost directly along the same line of sight as the mysterious Great Attractor and the even more distant Shapley supercluster. From our vantage point on Earth, these three colossal mass concentrations appear stacked behind one another, like mountains seen from a great distance, their peaks aligned. This alignment is not a visual trick, it is a fundamental clue to understanding the complex forces acting upon our own galaxy. Each of these structures, the nearby Great Attractor knot, the mid-distance Horologium Reticulum, and the far-off Shapley concentration, adds its own gravitational tug to the mix. Their combined pull, layered and reinforced by their alignment, creates a powerful river of gravity flowing in that specific direction. It is this cumulative effect that helps explain the precise speed and direction of our local group's peculiar motion. We are not falling toward a single point, but sliding down a slope shaped by multiple massive peaks in the cosmic topography. The Horologium Reticulum supercluster, therefore, is more than just a distant curiosity. It is a critical piece of evidence in mapping the total gravitational field that governs our journey. Its existence reminds us that the universe's largest structures do not act in isolation. They work in concert, their influences weaving together across billions of light-years to steer the destiny of galaxies, including our own, on a current set in motion at the dawn of time. But some of these ancient giants seem to defy the very timeline of cosmic evolution itself. Far across the universe, in the direction of the constellation Pisces, lies a structure that should not exist. This is the Saraswati supercluster, a sprawling, ancient metropolis of galaxies observed at a staggering distance of 4 billion light-years from Earth. When we look at it, we are not seeing it as it is today, but as it was when the universe was only about 10 billion years old, a mere adolescent compared to its current age. What we see is astonishingly mature. The Saraswati supercluster is not a loose, young collection of galaxies just beginning to cluster together. It is a fully formed, massive web containing at least 42 massive galaxy clusters, thousands of individual galaxies, and vast filaments of dark matter, all bound into a coherent structure over 650 million light-years across. Its name, drawn from an ancient Sanskrit word for a celestial river of wisdom, is profoundly fitting, for it represents a flow of knowledge that challenges our textbooks. The existence of such a colossal, evolved structure so early in cosmic history presents a serious puzzle. According to our standard models of cosmology, structure grows hierarchically. Small things form first, then merge over billions of years under gravity to become larger things. A supercluster of Saraswati's immense mass and complexity should have taken much, much longer to assemble. It is like finding the ruins of a vast modern city in an archaeological layer dated to the Stone Age. The timeline simply does not match. How could gravity have pulled together so much matter into such a coherent, massive form in what was, cosmically speaking, a relatively short amount of time? This supercluster suggests that the seeds for these immense structures might have been planted even earlier and been even more potent than we thought, or that some aspect of gravity or dark energy acted differently in the early universe to accelerate the growth of cosmic architecture. Saraswati stands as a fossil from the universe's youth, a relic that whispers our models of cosmic growth may still be missing a crucial chapter, a chapter written in the light of galaxies that gathered too soon. The Saraswati supercluster challenged our timeline, but the universe had an even earlier story to tell. Deep in the constellation of sextants, astronomers have looked back to a time when the cosmos was a mere toddler, just 2 billion years old. There they found not a mature city of galaxies, but a construction site of cosmic proportions. This is the Hyperion proto-supercluster, the largest and most massive structure ever identified from such an early epoch. It is not a finished product, but a supercluster caught in the act of being born, a direct window into the assembly of the cosmic web itself. Hyperion is a sprawling, chaotic web of at least 7 dense filaments, each one a river of young, gas-rich galaxies, all flowing toward several massive nodes where they are destined to collide and merge. Observing Hyperion is like finding the blueprints and half-built steel girders for a future metropolis, allowing us to witness the hierarchical growth of structure from the ground up. Its sheer size at such a young age is breathtaking, stretching over 200 million light-years and containing the mass of several thousand trillion suns. The significance of this discovery cannot be overstated. Before Hyperion, our models of the early universe suggested that matter should have been more smoothly distributed, with only the faint beginnings of clusters. Finding a proto-supercluster of this scale and complexity forces a dramatic revision. It tells us that the seeds for the largest structures were planted extremely early and grew with astonishing speed, likely aided by vast reservoirs of dark matter that provided a gravitational scaffold for the ordinary matter to flow along. Hyperion is a living fossil from the era of galaxy formation, a snapshot of the universe caught in a frenetic phase of construction, showing us that the great walls and filaments we see today were already taking shape when the cosmos was only a fraction of its current age. This colossal embryo holds the answer to how the diffuse glow of the early universe transformed with breathtaking rapidity into the intricate web-like architecture we now call home. The visible brilliance of a galaxy cluster is only a fraction of its true story. In the far southern sky, 4.7 billion light-years away, lies a titan that perfectly illustrates this hidden reality. This is ACT CLJ 01024,915, a galaxy cluster so immense and energetic it earned the nickname El Gordo, the Fat One. At first glance, its spectacle comes from two massive subclusters, each containing hundreds of galaxies that have collided at millions of miles per hour. This collision heats the gas between the galaxies to over 200 million degrees, causing it to glow fiercely in X-rays, a beacon of violent astrophysics. But the true source of El Gordo's immense power and scale is something we cannot see at all. Surrounding this entire chaotic merger, enveloping the hot gas and the speeding galaxies, is an immense spherical halo of dark matter. This invisible structure is the true skeleton of the cluster, a gravitational scaffold that holds everything together. We know it is there because of its effects. The immense mass of this dark matter halo warps space-time so profoundly that it acts as a gravitational lens, bending and distorting the light from even more distant galaxies behind it, creating stretched arcs and mirages in the deep field images. By measuring this distortion, astronomers can map the halo's shape and distribution, revealing a ghostly outline of mass that far outweighs all the visible stars and hot gas combined. This is the fundamental truth of the cosmic web. The luminous galaxies we chart are merely the glittering ornaments hanging on a framework built almost entirely from dark matter. These vast, invisible halos are the true cosmic continents, the gravitational anchors that first drew ordinary matter together after the Big Bang. Without this unseen architecture, the gas would never have cooled, the stars would never have ignited, and the great walls and filaments of galaxies would never have formed. El Gordo's dark halo is not an anomaly, it is the rule made spectacularly visible. Every cluster, every supercluster, every filament in the web exists within a similar, encompassing cloud of dark matter. When we map the largest structures in the universe, we are therefore tracing the shadows of an invisible world, following the contours of a hidden geography that dictates the shape of everything we see. Even the vast emptiness between galaxies is not truly empty. It is threaded with an invisible force, a whisper of magnetism woven into the fabric of space itself. Across millions of light-years, astronomers are finding evidence for large-scale magnetic fields, structures so immense they may trace the very filaments of the cosmic web. These are not the powerful, localized fields around stars or black holes. These intergalactic fields are astonishingly weak, billions of times fainter than a common refrigerator magnet. Detecting them at all is a monumental feat of cosmic detective work. Scientists use a phenomenon called Faraday rotation. As light from distant quasars travels through the cosmos, any magnetic field it passes through will subtly twist the polarization of that light, the direction in which its waves vibrate. By measuring this twist in the light from thousands of quasars coming from different directions, researchers can begin to map the magnetic landscape of the void. The emerging picture is extraordinary. These faint fields appear to be aligned with the colossal filaments of the cosmic web, as if magnetism itself is painted onto the universe's grand architecture. But how could such vast, organized fields form in the first place? The leading theory is a story of amplification and stretching across cosmic time. In the early universe, tiny, seed magnetic fields likely existed, perhaps generated by the turbulent motions of the first stars and galaxies. As the cosmic web formed and matter began to flow along the great filaments, these weak seed fields were caught in the current. Imagine a droplet of ink falling into a slow, immense river. As the river flows, it stretches the ink into long, thin threads, aligning them with the river's course. In a similar way, the billion-year flow of ionized gas along a cosmic filament would stretch and amplify those primordial magnetic fields, aligning them with the filament's spine and weaving them into a universe-wide tapestry. This magnetic tapestry, though ghostly in strength, may play a crucial role in the life cycle of galaxies. These fields can guide the flow of cosmic rays, influence the collapse of gas clouds to form new stars, and perhaps even regulate the growth of supermassive black holes at galactic centers. They are a subtle yet pervasive component of the cosmic ecosystem, a reminder that the spaces we once thought of as pure nothingness are, in fact, rich with invisible structure and silent, enduring force. This ghostly chill in the ancient sky remains one of the most tantalizing puzzles in cosmology. The cold spot in the cosmic microwave background, that region in Eridanus significantly cooler than its surroundings, acts like a cosmic fossil, preserving a mystery from the universe's infancy. While the supervoid hypothesis offers a compelling local explanation, the debate surrounding it reveals just how difficult it is to interpret the faintest whispers from the edge of space and time. The central question is one of scale and effect. Could a truly immense void, a sphere of relative emptiness hundreds of millions of light years across, actually cause such a pronounced temperature drop in the primordial light? The physics at play is subtle yet profound. As photons from the CMB travel through the later universe, they climb in and out of the gravitational wells created by clusters of galaxies and, conversely, the shallower pits of the great voids. Passing through an underdense region like the proposed Eridanus supervoid means the photon loses a tiny amount of energy as it exits, because the gravitational pull holding it back is weaker than average. This integrated Sachs-Wolf effect would make the photon appear slightly colder when it finally reaches us. The problem is one of magnitude. Detailed observations have indeed found a large underdensity in that direction, but many researchers argue it is simply not vast or empty enough to account for the dramatic cold spot we observe. The numbers for some do not add up. This discrepancy leaves the door open for far more exotic possibilities, ideas that stretch the boundaries of known physics. One of the most captivating, yet highly speculative, theories suggests the cold spot could be a bruise, a cosmic imprint left by a collision with another universe in a vast multiverse. In certain models of eternal inflation, where countless bubble universes are constantly budding off from a larger cosmic landscape, the boundaries of these bubbles can occasionally interact. If our universe had a glancing encounter with another in its distant past, the energy released at that boundary could have left an irregular, cold imprint on our CMB, a scar from a collision with a reality entirely separate from our own. While this idea is not the mainstream interpretation, its very consideration highlights the profound stakes of this mystery. The cold spot forces us to confront two equally staggering possibilities. Either our universe contains voids of such scale and emptiness that they challenge our understanding of large-scale structure, or the anomaly is a window into physics operating on a canvas grander than a single universe. Both paths lead to a radical rethinking of cosmic architecture. For now, the cold spot hangs in the celestial map, a cryptic patch of coolness that refuses to be easily explained. It is a reminder that sometimes the most important discoveries are not answers, but perfectly framed questions written in the oldest light there is, questions that compel us to look deeper into the chill and wonder what unimaginable geography might lie beyond. The universe's hidden architecture might be woven with threads of pure spacetime. Among the most fascinating theoretical constructs in cosmology are cosmic strings, hypothetical one-dimensional defects that could be longer than the observable universe itself. These are not strings of matter, but cracks or folds in the very fabric of reality, relics from a phase transition in the universe's first moments, like flaws frozen into ice as water cools. If they exist, their properties are almost beyond belief. A cosmic string would be thinner than a proton, yet a single inch of it could weigh more than Mount Everest. This inconceivable density would warp spacetime around it with immense gravitational force, creating a unique signature. Anything moving past a cosmic string would experience a double image effect, a form of gravitational lensing where light from a distant object is split into two identical copies, a telltale sign astronomers have searched for. Their theoretical role is profound. In the early cosmos, these ultra-dense threads could have acted as gravitational seeds, their immense mass providing the initial overdensities around which ordinary matter first gathered. The vast filaments of the cosmic web we see today, the great walls and arcs of galaxies, might trace the ghostly outlines of a network of cosmic strings laid down in the first fraction of a second after everything began. While decades of searching have yielded no confirmed detection, the hunt continues because their discovery would be a direct window into the universe's most extreme infancy. They represent a breathtaking possibility that the largest structures we observe are mere shadows, cast by flaws in the foundation of reality itself, one-dimensional scars from the birth of space-time. This brings us to the final and most encompassing structure of all, the one that contains every wall, void, and filament we have described. The ultimate cosmic architecture is the observable universe itself, a sphere of space with a defined diameter of roughly 93 billion light-years. This is not the entire universe, which may be infinite, but rather the portion of it from which light has had time to reach us since the dawn of time. Its boundary, called the particle horizon, is not a physical wall or an edge you could bump into. It is a horizon of information, the ultimate limit of what we can possibly know. Beyond that horizon, the universe continues, but its light has not had enough time in the entire history of existence to cross the expanding gulf and reach our telescopes. Every galaxy, every quasar, every great attractor we have ever catalogued exists within this sphere. They are all contained within this grandest of frameworks, a framework defined by two fundamental cosmic rules: the finite speed of light and the relentless expansion of space. This means our map of the cosmos is inherently a historical document. When we look at the most distant objects, we see them not as they are now, but as they were billions of years ago, often in their infancy. The observable universe is thus a kind of time capsule, with layers of history stacked outward in space. The Sloan Great Wall, the Hercules-Corona Borealis filament, the cold spot in Eridanus, all these are features within this colossal, dynamic sphere. They are patterns in the tapestry, but the tapestry itself is the sphere of the observable, woven from the threads of causality and light. To contemplate this is to understand our profound place within the whole. We are not just living in a galaxy or a supercluster or a vast web. We are at the center of our own observable universe, a unique vantage point from which we piece together, layer by layer, the story of everything. And that story, written across 93 billion light-years, tells us that the universe is not a random emptiness, but a place of majestic, organized, and deeply mysterious structure, from the tiniest quantum seed to the grandest horizon of all. So a clear pattern emerges from this menagerie of giants. The universe is fundamentally filamentary, a vast web of luminous threads surrounding profound voids. This cosmic web is not a decorative pattern. It is the essential architecture of reality, with galaxies serving as mere points of light along its dark matter scaffolding. Yet within this grand design, we find startling outliers. From the Sloan Great Wall to the Saraswati Supercluster, we keep discovering structures that push right up against, or seemingly step over, the theoretical limits for how large things can grow in the time available since the Big Bang. These are not just big, they are improbably big. Their immense scales hinting at a universe that clumped together faster and more efficiently than our best models predict. This tension forms the central puzzle of modern cosmology. How did these colossal filaments, walls, and superclusters assemble themselves within the framework of our standard model of the universe, known as Lambda-CDM? This model, which includes dark energy and cold dark matter, has been spectacularly successful in explaining a wide range of observations, from the abundance of light elements to the precise patterns in the cosmic microwave background. It tells a compelling story of cosmic evolution, where tiny quantum fluctuations in the primordial universe were amplified by gravity over billions of years, slowly building the web we see today. But the sheer size and maturity of some of these structures, especially the ancient ones like Saraswati or the embryonic Hyperion proto-supercluster, introduce a note of discord into that story. They act like clocks that seem to be running fast, suggesting the process of structure formation might have had a head start or an unseen accelerator. The dark matter framework is clearly essential. It provides the gravitational wells for ordinary matter to fall into. Yet perhaps the initial seeds were larger, or the dark matter particles interacted in subtle ways we haven't accounted for, or the influence of dark energy in the early universe was different. Each of these immense structures is therefore more than a cosmic wonder. It is a data point in a grand experiment, a test of our most fundamental understanding of how everything came to be. The universe, it seems, is not just showing us its size, it is asking us to refine the very story of its birth and growth. Our journey began with galaxies as the largest known things, but we ended seeing them as mere points of light in a far grander design. This transformation is profound. We have moved from a universe of isolated islands to a vision of an interconnected, dynamic web, a single flowing architecture where emptiness is as important as brilliance. The great walls and filaments are not just bigger versions of clusters, they are the fundamental highways and continents of the cosmos, shaped by dark matter and defined by vast voids. Every discovery, from the Sloan Great Wall to the hidden South Pole Wall, reinforces this new map of reality. We no longer live in a simple galaxy within a cluster. We are residents of the Laniakea supercluster, carried on a billion-year current toward the Great Attractor, all while being pushed from the Dipole Repeller within a local underdensity, all part of the Pisces-Cetus filament in the observable universe. This is our true cosmic address, a nested hierarchy of belonging on scales that continually stretch comprehension. This field of study is vibrantly alive. Each new, strange structure is not a final answer but a fresh question, a test of our cosmological models. The Saraswati supercluster asks how things grew so fast. The giant arc asks why the universe prefers certain shapes. And the cold spot asks if we are seeing a void or a scar from another reality. These are not puzzles from a finished textbook. They are the active frontier of human knowledge, where our most fundamental theories meet the raw, unexpected data of the cosmos. Every new telescope, every deeper survey, risks uncovering another anomaly that could bend or break our current understanding. This is the thrilling, humbling process of science at its best. A continuous conversation with the universe where we must be prepared to redraw our maps. So the next time you look up at a dark, starry sky, remember the invisible architecture that stretches beyond sight. You are not just looking at points of light, you are gazing at the luminous nodes in a web of staggering scale and beauty, a web that is still being charted. The story of these colossal structures is ultimately our story too, a testament to a curious species learning to read the grandest patterns of home. The mapping continues, and with it, our sense of wonder only deepens. Stay curious.